This is video 2 of our discussion of the chi-squared test, in this case of a probability density function. And we're getting right into section 2.2.5. Now, just to go over what we just covered, again, we looked at a pair of any two variables, okay, and it had some sort of theoretical or known function relating those two variables. And we learned how to characterize the misfit of our data from that theoretical curve. And conceptually, we learned how to test whether that misfit or the fit was significant. Here, the two variables will form a probability density function. So the variable on the horizontal axis is the, values of our quantity xi, and the variable on the vertical axis is just frequency. So this will be a frequency distribution function. And let's just say our test or a known curve is a simple curve that looks somewhat Gaussian. This is our test frequency distribution from the test PDF. Okay, so we'll take, so what we're going to do is test whether the frequency distribution of our data adequately fits that of the known PDF. And as you can see, it's a more sophisticated test than just the test of, say, the mean value or the standard deviation. It's going to test the whole PDF by comparing the frequency distribution of our data to the theoretical curve. So the first step we would do is we'll divide the range of x into k bins, and they can be of any size, or but there just has to be a fixed number of bins. We're basically going to make a histogram of our data, and in this example, I'll just break it into 5 bins. And you can imagine that as we do that, we're going to count the number of data points that fall within the range defined by those bins, and we're going to generate a histogram. And maybe it looks like this. But you can imagine if we were to repeat the process, sampling the same population, let's refer to this as the jth bin. If we were to repeat the process, the value in the jth bin might vary. Well, it won't be the same every time, right? Sometimes we'll get a value up here, sometimes down there, and so forth. Okay, so there's going to be some natural variability due to just incomplete sampling or even other processes that lead to the jth bin deviating from the expected number in based on the known or test PDF. So here we have to define our z variable. So z for the jth bin, and in general terms, again, that was x, our data value minus the expected or the mean value divided by the standard deviation. And in this application, the data is the observed number in the bin, mu is the expected number in the bin, and the standard deviation is s. So this is the observed number of data points in j, and this is the expected number of data points in bin j. So what is the expected number of each point? Well, to calculate the expected number of points, we just have to we get that information from the known or tested PDF. So the expected number of points in bin j is just equal to the total size of our sample times the probability of bin j. So pj is equal to the probability of x being in bin j. And that probability is just the area under this, in this case, the PDF under the blue curve. Okay, so that's how we calculate the expected number, but what is this S value? Somehow this S value is measuring the natural variability of a random sampling about this mean value. So how do we estimate that? Well, to give you a clue, and we've looked at this before, let me have you complete this sentence. So the probability of EJ data points successfully, and I'm going to highlight that word, falling in bin J with a probability of success of little pj follows a blank distribution. Okay, so we can cast the problem as saying that the probability of EJ successful points when the probability is PJ follows what sort of distribution is that? Okay, if you're thinking binomial distribution, then you're correct. The binomial distribution tells you the number of successes you're likely to get if the probability of a single success is little pj. So the other thing to remember is if n times pj is greater than 5 or so, then the binomial distribution is approximately normal. Okay, so that is to say that if NP is greater than 5, if NP is greater than 5, then the binomial distribution approximates the normal distribution. Okay, so we now have a variable that shows a normal distribution, and therefore if we square this variable, then it will have a chi-squared distribution. If we squared it and summed it over k bins, it'll be chi-squared. It'll have a chi-squared distribution of k minus 1. Okay, so back to how we estimate the variance about within each bin. If you'll recall, the approximate variance, Gaussian variance to the binomial distribution was sigma is equal to, sorry, this is the standard deviation. That's equal to the square root of n p little j times 1 minus p little j. So in general, it will depend on the probability of each bin. And for small p, this is about equal to n pj, and that's equal to the square root of ej. And that again is for pj a lot less than 1. So the standard deviation that we need, so again we have z again was equal to the observed number in bin j minus the expected number, and the standard deviation is now the square root of ej. So chi squared then becomes the sum of all those squared, and we can then compare this with the critical chi squared. And this test will always be one-tailed. So this is our chi squared for a given number of degrees of freedom. Because we only care about large values of chi squared, right? So we don't care about this tail where the chi squared values are sort of anomalously small, because that would just mean that we happen to find a data set that fit the distribution of the test population unusually well. Okay, to test, for example, whether the population sampled had a different PDF than the test population, then we care only about the high values of chi squared. All right, I better stop with this video. The next video we'll go over an example.